Hi, my name is Andrea Cromier, and this is Lab 5 for Physics 2. To introduce, the purpose of this lab is to develop a greater understanding of Faraday's law and how it relates a time-varying magnetic field to a curly electric field. We collect observational data of a falling magnet through a conductive tube and model this interaction computationally. To preview the results, the average time for the magnet to fall in real life is 1.10 seconds, whilst the time taken in a computational model is 1.155 seconds. So the fundamental physics principles we will explore are Faraday's law, which is essentially, as I mentioned, the relationship between the time-changing magnetic field and a curly electric field, which provides an EMF that can drive a current. This current also produces a magnetic field, which exerts a force on the source of the external magnetic field. Then we will also use Lenz's law, which states the direction of the current induced in a conductor by a changing magnetic field based on the law of energy conservation. These are some of the relevant formulas. Well, so I want to explain them. We will see these come quite often, especially in the computational model, and we should just make a note of them at first. So this is the experimental diagram, which is just a magnet falling in a tube. So moving on to the method, we essentially mark the North Pole using the magnetometer app, and then we drop it like vertically on a tube. Then we record this, and we repeat this recording 5 times in order to take an average. Some of the assumptions that are made for the physical model is that the magnet falls in a straight path, meaning that I dropped it exactly from the center of the tube, and it did not interact with any of the sides, so that the only interacting forces are essentially the magnetic and the gravitational force. The system includes the tube and magnet. And then this is some of the experimental data I measured, so I won't go through it, but this is it. And then for the magnetic dipole moment, it should be noted that I used the same one from lab 3 because it's essentially the same magnet. Then further calculations based on the experimental data are the following, and as we can see that this is just the average time, and the average time is 1.10 seconds. So some checkpoint questions. Why can't we use a ferrous tube? For example, like a steel pipe. Well, the ferrous materials contain iron, meaning that it can become an induced magnet when it would affect the falling magnet. Then what happens to the magnet, and how does it compare to a magnet falling in free space without a tube? Well, in this case, the magnet is being affected by two forces, the magnetic force and the gravitational force. If we were to drop the magnet outside of the tube, the only force affecting it would be gravity. Moving on to the computational model, here we know the constants and the initialization of the graph. Then we create the tube of aluminum foil using this code. And then we create the bar magnet. And here is where the formula for like creating like the rate of changing magnetic flux of the falling magnet, which is essentially the EMF. And then we create the simulation loop, which predicts the motion and creates the visuals. And here's where we see that F net is equal to gravitational force plus magnetic force. And we continue to update the bar magnet's velocity and position iteratively, which gives the following visual. As we can see, these is falling in the tube. And the time measured in the computational model is 1.155 seconds. And this is a graph. So if we interpret the simulation, we can understand that the intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. But how do we know if it corresponds to the clockwise or counterclockwise current? Well, the red is counterclockwise and blue is clockwise because the magnet slows down. And it is this combination that allows it if we consider Lenz's law. Then the current would flow in opposite direction to. Then what happens to the dynamic of the system when you flip the magnet around? Well, essentially the current will just change direction, like completely opposite to this model. And how does the total time in tube of the real world system compare to that of the computational system, and how can we improve it? Well, the computational system was fairly accurate. As we've mentioned, it is 1.155 seconds, which is fairly close to the in real life situation. So I think I did a good job with that. However, if I would change something, it would be to increase the amount of loops, because the closer it is to like an infinitesimal amount, the better it is. And then how does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Well, the forces are mainly unbalanced because of the steep curves. However, in this like 1 second where the curve is almost flat, it can be assumed that the forces are balanced. So some sources of error that are worthy of noting are that the computational model does not account for error resistance, and it also accounts for like a finite number of loops. Then it also should be accounted, like human error should be accounted when timing the falling magnet in real life. Moving on to the reflection, what if the resistivity of the conductor were reduced as close as possible to zero, and how would the dynamics of the falling magnet change? The braking force would increase, where it would balance gravity and prevent the magnet from falling through the tube. And then what if holes or slits were cut into the tube, and how would this affect the rain currents in your model? Well, holes and slits would interfere and reduce the flow of current in the tube, which would cause the braking force to decrease in strength, and the magnet would fall faster, being mainly influenced by gravity. Thank you.